All right, so for this video, we are going to look at the roots and radicals notes. Just a quick little intro. When we talk about a root or a radical, we're talking about things like the cube root of 27, which could be evaluated down to equal 3, since 3 cubed gets me back to 27. 3, this little 3 here is called my index. It tells me what type of root I'm looking at. 27 is called the radicand, the number under the radical. We're going to do 4 different things here with our radicals, just sort of basics things: simplifying, multiplying, dividing, adding, subtracting, and rationalizing here. When you're simplifying a radical, you're trying to get this rewritten into an equivalent form, but to remove any components of it, any factors of it that are perfect squares, and get those simplified into integer form. So just real quick, I'm going to make a list of my perfect squares. These are numbers that I can square root, so like 1, 4, 9, 16, 25, etc. What I look at is I will try and think, are there any of these numbers that would divide into 28? And the answer to that is 4. So I'm going to rewrite this as a product of the square root of 4 times the square root of 7. Square root of 4 happens to equal the integer 2. Square root of 7 I can't evaluate any further to an integer, so that will just be 2 square root of 7 there. I often will write the square root of 4 first so that the 2 comes out in the front, since you want the coefficient to be up at the front there. On this next one, I'm going to consider first just the radical portion. Rewrite the square root of 12 as the product of the square root of 4 and the square root of 3, since 4 times 12 gets, or excuse me, since 4 times 3 gets me 12. I'm going to leave this 5 up at the front. Square root of 4 is equal to the integer 2. Square root of 3 I can't simplify any further, so then I can multiply 5 and 2 and get 10 square root of 3. When we're multiplying and dividing, your index must be the same, which means you have to multiply square roots with square roots, cube roots with cube roots, and then coefficients like 4 and 3, you can't multiply with numbers under radicals, aka radicands, but you can multiply those numbers with one another. So in this example, square root of 2 times square root of 12, I am allowed to multiply those numbers since they're both in radicals. I would end up with square root of 24. But then I should also check this to see if this can be simplified. Since I can rewrite this as the square root of 4 times the square root of 6, and since 4 is a perfect square, I am going to be able to simplify this. Therefore, this would equal 2 square root of 6. 4 times 3 in this one would get me 12. I'm allowed to multiply those both since they're coefficients and they're outside my radical. Square root of 2 times the square root of 5 would get me the square root of 10. Since the only factors of 10 are 2 and 5 and 1 and 10, there are no perfect squares that can divide into this, so that's as far as I can simplify that. On this example, the coefficients I'm allowed to divide, and just get whole number 3. And then the root portions I'm allowed to divide since they both have the same index, so I get the square root of 5. Moving on to adding and subtracting, the key here is that the actual radicand must be the same. So the radicals have to be identical in order to add or subtract. Think of it like if I had 6x plus 5x minus 2x, and you'd be thinking about this as if they were like terms. 6x plus 5x would give me 11x, minus 2x would give me 9x. So in the same respect here, 6 radical 7 plus 5 radical 7 would be 11 radical 7, minus 2 radical 7 would be 9 radical 7. If I'd had one of these radicals as a different number underneath there, you would not have been able to add and subtract them. And then finally, with rationalizing denominators, your goal is to get the radical out of the denominator, but without changing the value here. So you're going to multiply strategically by the radical that already exists there. So I'm going to multiply by radical 5 to match this one on top and on the bottom. Since I'm multiplying by the same thing, I won't have changed the value. I can't multiply 2 and 5 together to get 10, so I'll just put 2 in front as a coefficient. But I can multiply the square root of 5 times the square root of 5 and get the square root of 25. which then simplifies to the integer 5. On the top, I'll have to choose square root of 5. Because this simplified to 5, no longer with a radical, I've successfully rationalized my denominator. And making that happen was why we picked this radical to begin with. So down here, I'm going to pick just the radical to multiply by. Again, I can't multiply those and get 15, so I'll keep 5 radical 3 on top. I'll get 2 radical 9 down here in the denominator. 2 radical 9 will become 2 times whole number 3, which will become 6. Then I should finally, at the end, check to see if this can be simplified at all, since I've now created a new kind of fraction combination there. Since there's no reducing or simplifying I can do with 5 over 6, that would be as simplified as that expression could be. At this point, you should be able to try the next couple examples, examples 1 and 2, and at least get those started, and I'll go over those in the next video.